Okay, and we're back. We've got this mathematical description of the traveling wave, and we explored that just a second ago on the whiteboard. But the picture of standing waves requires, if both ends are fixed, that at each end that there is a node. The largest possible oscillation that fits between the two ends, we can call that the fundamental, whether that's the longest possible wavelength that can exist between one end of the string where we're holding it and the other where it's attached to the wall. Other wavelengths could fit shorter ones if one full wavelength exists between where we're holding it and the wall. That means there's a node at the middle where the sine graph crosses the axis on its way down and then comes back up. So we get that crossing in the middle, and we get a node there and two antinodes. What if we had a wavelength and a half that fit between our hand and the point on the wall where it's fixed? So we get sine up through 0, down and back. And then we could have another half a wavelength like we had here. We only had up, back to 0. The full wave would need another trough and then back to 0. So initially we only had half of the longest possible wavelength that we can fit. Here in figure C, we've got 1.5 wavelengths of this particular wavelength. But if you'll notice, from figure A to B to C, the number of antinodes goes 1, 2, 3. So these are like first mode, second mode, third mode, I guess. The fundamental, and we number them according to the number of antinodes or the harmonic. The fundamental, or the first harmonic, the first overtone, the next highest frequency, because the shorter the wavelength, for the same speed, the higher the frequency needs to be. And they are just integer multiples of each one. So whatever the fundamental is, the next frequency that fits between these two ends is 2f1, the next one is 3f1, and so on. So we get a pattern of wavelengths and frequencies. 2L, L being the length of the string, divided by N, where N is the number of the frequency we're talking about, the number of the harmonic. 1 for the fundamental, 2 for the first overtone, and so on. Here again, the speed divided by that wavelength, and we can plug in that expression, and we end up with the integer of the harmonic number times the frequency of the fundamental. Air columns work in a similar way, unless we have one end closed, and I'll explain that in a second. If we have a tube with that's open at both ends, in other words, that is not fixed at either end, we can get the same stuff to happen as long as we insist that there's antinodes at each end. There's no fixed point on the wall for the wave to terminate at. It's got to be, I mean, if it's a maximum amplitude, then it's running into the walls, the diameter of that tube or whatever. So the antinodes show up on either end, but the pattern of frequencies is the same as it is for a string fixed at both ends, for a column open at both ends. For an air column open only at one end, the story is a little bit more complicated. We need a node at the wall and an antinode at the opening. So we're actually able to fit only the first from, if we think about a sine graph, from 0 up to 1 and then back down to 0, but in this case we start 0 at the node and we can go up to a maximum. We're done. That's only a quarter of a wavelength. In other words, a quarter of a wavelength fits in the length L, so the frequency is what it is. The next shortest wavelength that fits is 3/4, right? If we try a half, then the picture wants to have a node at the end of the graph, but we can't do that. We have to have an antinode at the open end, so we can only fit a 3/4 wavelength is the next shortest wavelength that fits in the thing. So we skip the numbers. There isn't an F2, only F3 speaks. There is no way for the frequency that is double the fundamental to exist. It can't fit in the tube. The next frequency that we see is F3, 3 times the fundamental. And then the next one is 5 times the fundamental. So in this case, only odd multiples of the fundamental frequency are possible. Different instruments sound different to us. Clarinet sounds very different from a violin, which both sound very different from a piano. And the reason for that is that not only one of these frequencies is emitted. A piano string that we, hit with a hammer oscillates with many different frequencies that are all associated with this overtone series, the harmonic series. It's the relative amplitudes of the various components that make a sound like it does. This is a neat picture, but I've got a little demo that I'll link you to that I think might be helpful. And that's this one. Fourier analysis, Fourier, Fourier, is essentially about the combination of things of different frequencies to achieve some picture overall. Okay, so I am hoping that that single frequency tone is audible to you. And what I'm about to do is add additional frequencies in the harmonic series at particular amplitudes. Eventually, we're going to put together sound that sounds differently than this. And if we only add a few frequencies, we can really see the difference. I'm going to turn this volume up to make sure that the microphone can hear it. This is obviously very, very different. There's this higher pitch in the sound that we can definitely hear. I'm going to actually turn the volume down a little bit because it's going to get very loud for me. This is just tracking amplitudes. 25463, 0.4244, 1.27. If we add more, we change the character of the sound that we're hearing. The more we add, the more this starts to sound like the more frequencies we add, the more this starts to sound like a sound effect from some really old video game, or some like the Super Mario theme is like 8-bit sound or something. Just add a bunch and see what this sounds like. You get this really sort of sharp sounding, electronic sounding. Okay, that's enough of that. But that's a demonstration of what this slide is talking about. The different instruments, different sounds have different frequency content at different amplitudes relative to each other, and that's why they sound different to us. It's why one person's speech sounds different than another person's. There's different frequency content there. Sound waves can interfere just like any other kind of wave, and we talked about this last week. If you have a speaker, a computer, try this trick with the demo that I just used. Play only one or two, maybe only one tone, just so that it's nice and pleasant to listen to. Turn the volume up and then walk around your room. I suspect that you'll find points in the room where the sound feels louder or quieter. And that's just because the sound coming from the speaker is interfering with the sound coming from the reverberation off the walls, and the environment itself is changing the way that the wave is perceived at each of those locations around the room. Another way to sort of to see this interference phenomenon is the phenomenon of beats. If we have two frequencies that are only slightly different, then the interference, as one of them goes faster than the other, we can think of it, then sometimes that one is going to line up ish, and we get a kind of a loud spot. But sometimes the slightly faster one, it'll go a little bit faster, and it'll get to a point where the slower one has a minimum, has a trough, where the fast one has a crest. And we end up with attenuation. We end up with a quieter sound than we have in either one. So we get these patterns of constructive and destructive interference as time goes on, and we hear that as beats or as frequencies out of tune. If you've got a lot of pianos have two strings for each key, and if one of them is out of tune, that's the thing that happens when you say, oh, someone's playing the piano and you get this out of tune chord or something like that. That's what's going on, is these two strings don't quite sound at the same frequency anymore. I've got another demo. Okay, so we've got these two different, the blue and the red, two different sounds. One of them has a frequency of 250 cycles per second, hertz, HZ. The other one has a frequency of 240. So they're only 10 hertz different. And if we overlay them, you can see periods where they essentially are trying to do the same thing, where we get constructive interference and we get a loud spot here. We can also see periods where basically anytime the blue curve has a crest, the red curve has a trough. And that's periods of sort of maximum destructive interference, and we get quiet spots. So we get something somewhere about the same frequency, somewhere in the 250, 240, 245 kind of range, but it's attenuated, modulated by this very long sinusoidal thing. The envelope is modulated, not unlike what we were talking about as far as standing waves, where we had, a spatial picture modulated in time. The other way to think about it is a full oscillation modulated in space, that as space goes, we trim and we have a low spot and a high spot. If I turn the sound on, we'll be able to hear those beats, that it'll sound like a pulsing. If we change the difference between those frequencies, we can change the way that sounds to us. As we make those frequencies closer to the same, we include more of a region where, like, the region where they line up is larger, and the region where they don't line up, where they anti-align, is also larger. So we're spreading out those periods of maximum amplitude and minimum amplitude. If two instruments are playing at different frequencies, we'll be able to tell, because our ears can detect those differences. The period for this one is so long because they're only a tenth of a hertz apart. That's enough of that. Go back to slides. So we talked about beats. There's one more funky sound I'm going to end up playing for you, and it's the sound that has to do with the Doppler effect. Because the speed of sound is relatively low, on 343 meters per second or so, it's possible that a source that's emitting sound, might be moving fast enough to bunch up the crests in the direction that it's moving. So on the side of the picture that the fire truck is moving towards, that frequency those wavefronts get sort of bunched up a little bit, and the wavelength decreases. If the wavelength decreases, the air is the same, so the speed of sound in the air is the same, which means the frequency has to increase. This person on the right-hand side is actually hearing a higher frequency than ordinary, than if the truck were at rest. This person on the left is hearing a lower frequency because those wavefronts are spaced farther apart. My favorite example of this is ice cream trucks. any sort of like confectionery delivery truck, right? As it goes, it's playing this song, right? And as it goes by you, the frequencies all melt and it sounds all demented and weird. As the ice cream truck passes us, we can hear that the pitch, the apparent pitch, decrease because it's moving away and those wave fronts are getting farther apart. Where the whole song just sort of melts down to a lower note. What's the math for this? That's the last sort of media that I want to link us to. So I'll use the slides again. Presentation mode. Okay, there we go. Okay, so we've got our moving source, and it's emitting waves. We're going to track them with the wave fronts or the crests. When the source was at point 1, it emitted a wave, a crest, that in some amount of time has gotten to here. In that amount of time, the source has moved from point 1 to point 2 when the next crest is about to be emitted. So the apparent wavelength, the distance between one crest and the next one, is way shorter than it would have been. It would have been all the way from this crest back to point 1. Okay, so it's shorter by the amount that the source has traveled in that amount of time, one period, because the next crest is just emitting. So that distance is the distance by which we are decreasing the wavelength. And there it is. The actual wavelength, the distance between what the crests would have been, is decreased by an amount equal to the distance that the source travels during that amount of time, capital T. And then if we plug in for what we know about the relationship between the speed of the sound and the wavelength, we can express it in this way. And we can express the frequency because it's the pitch that we hear, right? We don't really see the wavelength changing, we're hearing it because it's sound. So it's the pitch that we can really perceive. As a source moves towards us, the frequency we observe, F prime, increases because we're dividing by a number smaller than 1. So divide by a half, we end up multiplying by 2. If the source is moving away from us, because we change to a plus sign, the denominator is larger than 1, and we end up dividing by a number larger than 1, so that decreases the apparent frequency that we observe, F prime. We could do the same trick if the observer is moving. It's a similar sort of thing. And we end up doing a similar analysis, and we can say that the observed frequency, if an observer is moving towards a sound source, is greater because we're bunching up again the wave fronts. So the plus sign here. If the observer is moving away from the source, then we have to decrease the apparent frequency. So we multiply by a number smaller than 1. If the source moves too fast, it outpaces the wavefronts, and we can end up with a shock wave where the wavefronts cannot keep up anymore. We're actually going faster than they are. And there's these lines where all those crests exist kind of together all at the same time. And the shock wave, we call it. And the angle that it makes is given by the ratio of the speed of sound in whatever medium it is we're talking about and the speed of the source. You could think of this kind of like the wake made by a boat in water. If the boat is going faster than the wave speed in the water, then we actually see that trail of, it's the shock wave. It's that sort of line of crests that all exist at the same time, even though they were emitted at different points at different times. They all exist here at the same time. For our purposes, it's mostly observable whenever, like most of the time when we're seeing this phenomenon as humans, we're seeing it as experiencing when a supersonic jet goes by, anything faster than the speed of sound, and we get these shock waves, these booms. Since we've said all this about sound and how it behaves, what can it do for us? Bats and other animals use sound and the reflections of sound off of nearby objects in the environment to navigate. And we can do the same thing, send sound into, let's say, like an underwater environment and watch the reflections that come back to figure out how deep a body of water is. That sound has to get down there and then come back. If we know how fast the speed of sound is and we know how much time it takes, we can figure out how deep that body of water is. There are medical applications as well. If we use ultrasound beyond the frequencies we can hear, we can detect echoes in that sound as made by organs and bones and things in our bodies. And so as the incoming pulse encounters the edges of different media within the body, organs and things, we get echoes when we make those transitions from one a medium of one speed to another. And those reflections come back, and their amplitudes, depending on how much reflection there is, lets us figure out, well, what was it that we encountered? Was it an organ or was it a vertebra? And we can develop a pattern of traces like this, of different echoes that come back, put those traces together and end up with a picture of the bodily environment. And that's all we have to say about sound. Along with this, I'll post this week's worksheet and this week's lab, and we'll go from there. Thanks, everybody. See you next time.